Hello everyone, here we'll be discussing 7.5, which is a section on strategy for integration. To be quite honest, this section really is just a summary of 7.1 through 7.4 strategies. Here we'll actually be seeing a few examples that are pretty challenging integrals, to be honest, where we have to think and see which of the strategies we've seen from 7.1 through 7.4 are actually applicable. Now there are some key strategies here that I want to first bring to mind. Is that we should simplify the integrand when you can and consider substitution. In fact, very often you want to consider what is called an obvious substitution, and some key guidelines I've given you for substitution are you want to consider either a definite inside, which is the most obvious, maybe a denominator, something inside the denominator or the whole denominator, maybe a power. In fact, I've even seen some integrals where if you let the whole integrand be u, you actually get some progress, believe it or not. And then here I have an empty spot because, well, sometimes nothing works and you just have to try different things. And what that entails, well, we'll kind of see that in a few examples. But these are some things you want to try before even thinking about the main sections we've discussed, which of course are integration by parts, integrals involving trig functions like a power of sine times a power of cosine or something like that. Trig substitution, where it doesn't involve trig, but then you convert it to a trig integral involving some substitution. And then 7.4 was partial fractions, where you have a rational function. So polynomial over polynomial, if you can factor the denominator and it doesn't seem to be integrable in an easy way, then you might want to split it up, use the partial fractions, and you should be set. Okay. So here we're just going to start with some examples, and then we're going to just talk through the process and the thought process behind how I get from one step to the next. So here, well, there's a power of e radical x. So if I call that u for a u substitution, maybe that works. Something we can also try for a u substitution is maybe u equals the whole thing, but we'll discuss that in a second. I think that's not a bad idea, but let's see here what happens. So if u is radical x, notice that's the same as x to the 1/2, then that means its derivative is 1/2, well, x to the negative 1/2. In other words, it's 1 over 2 radical x. So I'm going to leave it like that if that's okay. Now something funny that kind of happens sometimes, and here we kind of see it happen a little bit, is that du is described in terms of, well, x usually, because u is in terms of x, but it's self-referenced in this case, because notice, since u is equal to radical x, we can actually write this as 1 over 2u dx. Now, of course, we don't have 1 over 2 radical x in this integral at all. We, of course, have no u's in it, but we can solve for dx always. So if you solve for dx in terms of u now, then 2u du is going to be equal to dx in this case. So let me just get rid of that circle for a moment. I'm going to box all this because we're going to use a lot of information here in the substitution to see if we can make any progress with this integral. Now, when we make the substitution, notice that the exponent gets replaced with u, so this is now the integral of e to the u. Dx gets replaced with what? So let me try to border this off a bit. Dx gets replaced with 2 du, 2u du. Notice 2 is a constant, we can pull it out of the integral. And what we have left, e to the u times u, or u e to the u, this is a classic integration by parts problem, of course, because you have a polynomial or a power of the variable multiplied by e to that, so by an exponential. In fact, a very similar thing occurs if you have a power of the variable multiplied by a trig function. Anyways, we can use actually tabular method here, which is just a quick version of by parts that works sometimes. So we have derivative column, antiderivative column. We're going to take the derivative of the power of u, which is just u to the 1. Its derivative is 1, derivative of that's 0. Then we take the antiderivative of e to the u, which of course is itself, all the way through. And we multiply these diagonally, change their signs accordingly, and we end up with just 2 times the quantity u e to the u minus e to the u, and then plus c finally. If we distribute the 2, then we can do that. But notice what is u? U is radical x. So I'm going to take this time to actually replace it back with what it was equal to, radical x. And I said I would talk about what would happen if u was equal to the whole thing. So let me do that in red below, actually. So let's just ask ourselves what would happen if u was equal to the whole integrand e to the radical x. Well, if u was equal to e to the radical x, then du, its derivative, would be what? Well, derivative of e to anything is itself, but then you have to multiply by the derivative of the power by chain rule. And we already saw derivative of, well, radical x is this, so we end up getting a, well, essentially a 2 radical x in the denominator and then dx. Okay, so the really nice thing about this is that actually the numerator here, e to the radical x dx, is equal to the whole thing. So you can replace it with 2 radical x times du. So in other words, if you multiply that 2 radical x to the other side, you get 2 radical x du is equal to e to the radical x times dx. Now that may not sound very exciting because here we're replacing this with this, and this has a mixture of x's and u's. But remember what I said here, it's self-referenced. So maybe there's a way we can write radical x in terms of u. And there kind of is. Basically, if you take natural log of both sides here, you get ln of u is equal to radical x. So this is 2 ln of u du. So the inside really becomes this, which can be done also by integration by parts. The substitution is a little different though, and then from there, when you back substitute, you'll get the same exact thing anyways. So it's nice to see that different substitutions can possibly work. Some are more obvious than others. Like I think this is more obvious because it follows the guideline I given you before to power. So that works. Over here, well, notice we have a definite inside, that's the inside of the radical. Of course, we also have a denominator. So again, we can try different things, and for all we know, a substitution you use may work opposed to one I'll use. Well, I mean, they both may work. But you may try something completely different from what I try, and it will still also work, but just in a different way. And that's okay. In fact, I encourage that. So here, let's let u equal the inside of the radical, ln of x. And this is honestly something we've seen a lot before in well, just when we would start u substitution. If u is equal to ln of x, then we get 1 over x dx. And notice we have a 1 over x dx here. So those get replaced with just u. In fact, that's really all we need from our substitution. So we're good to go. And then we just end up getting 1 over x dx is replaced with du. Ln of x in the denominator, well, in the radical in the denominator, get replaced with u. And notice radical u is u to the 1/2, 1 over that's u to the negative 1/2. So this is really this. And now finally applying the power rule for antiderivatives, we get u to the 1/2 divided by 1/2, or 2u to the 1/2, or maybe even better, 2 radical u if you like. There we go, sounds better. And since u is equal to ln of x, sorry, there's no du because we took the antiderivative, so maybe plus c instead. So now we can write this as 2 radical ln of x plus c. And then of course you can check these. That's the beauty of indefinite integrals. You can always check your answer by taking the derivative and seeing that you indeed get the integrand you started with. Okay, now we're going to look at some more challenging types of examples, and that's really all 7.5 is about. But again, we're going to talk through the process. Right, so for this example here, this is a rational function known as polynomial over polynomial. As it turns out, the denominator here is actually factorable, so maybe you can think of a way to set up a partial fraction decomposition. But to be quite honest, the way this is factored is a little too much. I mean, I guess I could show you real quick, but you'll see real quickly that it looks a little too crazy, and there must be a better way. So I'll just show that real quick how you would factor the denominator in this case. At least one of the ways I know to factor the denominator. So if you were to actually consider adding and subtracting 2t squared in the denominator, what you can do is just adding 0, which is often known as a mathematician's favorite trick. This should look familiar. This is just t squared plus 1. And this, of course, is a square itself. It's radical 2 times t all squared. So by difference of squares, this is t squared minus radical 2t plus 1 times t squared plus radical 2t plus 1. And each of these, radical 2t I meant to say. Yeah. Again, it's because difference is squares, so I'll allow you to kind of fill in the details on your own, but That I think is pretty clear. Now, of course, each of these are irreducible quadratics. You can't factor each of them because the radical kills it, basically. And from here, if you factor the denominator like this is just really the third case of partial fraction decomposition, where you would have at plus b over this plus ct plus d all over this, and then you can use either equating coefficient techniques or Heaviside method or something to find a, b, c, and d in that case, but that gets a little wild. But at least I thought we'd kind of see it because it's nice to see that that's something you could do, and at least it comes to mind because it is a rational function. Yeah, so I'm not going to do that. You can try that if you want. If you want to do that, that's fine. The next thing that comes to mind is that this is it looks very much like what it wants to look like, or what I would like it to look like, is t squared plus 1. If it was t squared plus 1, then trig sub comes to mind. Remember, you always want to consider trig sub when you have a variable squared, either added to a number, subtracted from a number, or minus a number, something like that. But in this case, it looks very much like t squared plus 1. So can we make a t squared? Well, we can replace it with u squared. So if we replace t to the 4th with u squared, what would that mean? Basically what that means is you want to replace u with t squared. Which makes sense, because if u is t squared, then that means t to the 4th would be u squared. And we would indeed get u squared plus 1 in the bottom. And it looks like, well, we would replace the top maybe with radical u or something. But as it turns out, if you use a substitution, the really nice thing is that du ends up being 2t dt, and we have t dt here in the numerator. Let me just circle that in red real quick. Just like that. And from there, I think we're golden, but let's see it happen, shall we? I think we're okay to do that. So again, using the substitution, the t dt gets replaced with 1/2 to u. We can pull the 1/2 outside of the integral. Then we have du. Left over now is 1 over t to the 4th, as we said earlier, is going to be t squared squared, which is u squared plus 1 in the bottom now. And this is a simple antiderivative. In fact, if you don't remember this, I'll just tell you. This is arctangent or tangent inverse of u. So this is 1/2 tangent inverse of u plus c. Now it's, again, of u, but u is t squared, so I guess we're done really here. So that actually wasn't too bad. That was just a trig substitution. But at least we saw the thought process as far as how we can see that it's a trig substitution, because we have an even power plus a number. Okay. This one, you can try to do a few different things. If you wanted to, you can try to let the inside be u. Let's do that. Let's see what happens. So if u is the inside, I don't think this is going to be really pretty. Why? Because to find du, we would need a quotient rule, and we would get something over the bottom squared. That sounds ugly. I'll try it anyways, just for good measure. But it's going to be all over the bottom squared, so 1 minus x all squared. Now, if you don't recall quotient rule, it's very much like product rule, only instead of taking the derivative of the first part first, we'll take the derivative of the top first, and there's subtraction instead of plus. So just follow me, it's derivative of the top times regular of the bottom minus the other way around, regular of the top times derivative of the bottom. Now derivative of the bottom is -1, so that changes this to plus. And what's nice here, if you ignore all the parentheses that we don't really need, the x's actually cancel out, and we get 2 over, and this is times dx. So we get 2 over, let me just clean this up a bit, the denominator squared. So this, though, looks kind of pretty, I don't think we can really use it in any way, shape, or form. Unless we had, I'm trying to think how we can make this work. I mean, if we had a 1 minus x squared on the bottom, then maybe we can use, not even actually. Because if you multiply top and bottom by 1 minus x, that's interesting to look at, because on the top you'll have 1 minus x squared, which kind of reminds us of trig substitution, but since we're using this substitution here, that kind of goes out the window. But I think that idea, though, still comes into play. So honestly, this substitution ends up being a little useless. I don't see any progress here at all. If you want to try something using this, you can try, but I don't think it's going to work. What we could do instead, though, is we can again let well, before we consider U substitution, let's treat this as radical over radical. So basically what we're going to do is we're going to rationalize the fraction. And it doesn't actually matter if you rationalize the numerator or the denominator, but I'll rationalize the denominator. So I'm going to multiply top and bottom by the radical of, well, 1 minus x. Or should we rationalize the numerator? Honestly, you can try either and see what happens. I honestly think either is going to be okay. Yeah, so something else is also coming to mind that may or may not work, but no, actually that won't work. I'm just thinking out loud. But I'll explain what I'm thinking in a second. But now notice when you do this, the denominator becomes this square, so the radical cancels. So let me write this here. We just get x minus 1 outside of a radical now. On the top, really we have inside the radical this difference of squares, because it's 1 minus x times 1 plus x, so that's just 1 minus x squared, but now inside the radical. And this is a perfect example, or perfect candidate, I guess you can say, for trig substitution, where x is equal to sine of theta, because 1 minus sine squared is just cosine squared. So here we're going to let x equal sine theta, so that dx is equal to cosine theta d theta. And I'll leave it up to you to figure out what would happen if you were to do it the other way around and rationalize the numerator instead of denominator. But I think this is okay. So this is all we need for this substitution in this case. So we'll get 1 minus sine squared on the inside of the radical, which is just cosine squared. The square root of cosine squared is just cosine, so I'm just going to leave those details up to you because we've seen that a bunch of times already, hopefully by now. The denominator will be, ugh, you hate to see that. The denominator is going to be sine minus 1, which looks a little weird. And the numerator, well, we already dealt with the numerator, but the differential part, dx, is replaced with cosine theta d theta. In other words, this cosine and this cosine join to form cosine squared. Okay, so that's not too bad, but it looks a little strange. Maybe it was best to have it the other way around, because if we had it the other way around, then we'd have a difference on top. So as it turns out, we actually, I think, have to do it the other way around, or we should have rationalized the numerator, not the denominator. But that's a quick fix, so let's just bear with me, let's see. So that would be multiplying top and bottom by this, so that the top is 1 plus x, like that. The denominator now will be that difference of squares, so that's going to be radical 1 minus x squared. And the beauty here is that it would actually be, believe it or not, it would be the same. It would be the same substitution. And in fact, basically there's a way to save this, and that would be by multiplying top and bottom by sine plus 1. Because sine plus 1 times sine minus 1 is the difference of squares, and it's sine squared minus 1 squared, which is just sine squared minus 1. Since 1 minus sine squared is cosine squared, then sine squared minus 1 would be negative cosine squared. So this would actually turn into cosine squared over negative cosine squared. They cancel, but you'd have an additional sine plus 1 on the top. But in any event, using that substitution with this new integrand will give you the same thing anyways. So it's kind of funny to see that you can actually save what we had. But this, I think, is just a better way of doing it. So we're going to have, again, the radical part becomes just cosine. We saw that already. Okay, and the numerator now will be 1 plus sine theta. The differential part is cosine theta d theta. So these actually cancel out instead of combining like we had before. Perfect. Why is it so perfect? Because we can take the antiderivative really, really, really easily. Just take the antiderivative of each term. We get theta plus, no, minus, antiderivative of sine is negative cosine. And then plus c. Now we're not done. The trickiest thing about trig substitution that most people hate, honestly, is that when you have to back substitute, you mainly have to consider a right triangle, which honestly helps. If you don't do the right triangle way, there is a way of doing it, but it's not as intuitive. So I'll kind of show you a little bit. So notice x is equal to sine of theta, so that means theta is x, well, the sine inverse of x. So the first term is sine inverse of x. Minus cosine. Now, again, since x is equal to sine, then cosine, as we saw, was just radical 1 minus x squared. So in fact, this cosine is just 1 minus x squared inside the radical like that. So this really is the answer. And I know I did that last part kind of quick, but again, if you consider the triangle, the right triangle that's associated with the substitution, since sine of theta is equal to x, you can think of that as x over 1, and notice sine is opposite over hypotenuse, then this by Pythagorean theorem would be radical 1 minus x squared, so the cosine would be the radical over 1, which is just the original radical in our equation before we, or in our integral before we considered our substitution. Great. So this is it in this example. One thing I kind of pondered for a moment and then I agreed it wouldn't work was that if you made these the same, because remember our original thing was all under one radical, and if you made them the same, then you would want there to be a negative x on top instead of a positive x. So there's kind of a way of doing that, just to show you. So I would want this to be minus x instead of positive x, but notice if you add 2x to that, you get back to 1 plus x. So the benefit of doing this, of adding, basically adding and subtracting x in the numerator and joining it like this, is that you can actually split this up as that over 1 minus x and that over 1 minus x. And then of course this is 1, so you'll get 1 plus this. And then there may be a way to continue from there, but I tried thinking about it a little bit. I don't think this will actually work. It's not a bad idea though if you want to consider a u substitution, but remember that a fraction or rational expression being u is generally not a good idea because you'll have a denominator squared and that doesn't really lead to too much progress. Okay, so we're going to see only a few more examples now, and again they're going to be kind of challenging. These ones are getting there, but these next ones should be pretty challenging now. All right, it may be a little ambitious, but I want to finish the video off with these 4 examples here. Now these 2 will take a little bit more time and space, so I'm just going to handle these real quickly. These 2, they're actually pretty challenging and they're alright to be honest, but what we're going to do is I'm just going to get you started, and then from there I'll kind of explain without actually finishing it off, and it'll be a nice exercise for you to finish. These 2 we'll do in detail though. So for this one, I mean it's kind of hard to say, but remember when you have a power plus a number, power of x plus a number, you think trig substitution. But remember I said even power. So basically this is not an even power, it's an odd power, so what do we do? Well, if we just kind of force it, so if we force x cubed to be even, so what do we want to replace x cubed with? Well, in a trig sub we would like to replace x cubed with tangent squared in this case, so the tangent squared plus 1 is secant squared. So let's just write the substitution x squared is equal, or x cubed is equal to tangent squared. Now, if you find the differential like this, it's going to be a little weird, so we can actually square root both sides, but only consider positive roots, of course, and then we take this as x to the 3/2 equals tangent theta. And if you take the derivative of this, you just get 3/2 x to the 1/2 dx, and derivative of tangent, of course, is secant squared. And this may seem a little weird at first, but this is actually on point. This is super on point. Why is that? Because notice, x to the 1/2 is just what? It's just radical x dx. And there it is right there. So radical dx is just replaced with secant squared theta d theta. And this actually becomes even crazier because notice what our x cubed plus 1 becomes in the denominator is just, well, remember we want x cubed to be tangent squared, and that's the case here when you take, I guess, this to the, a little hard to say in words, but basically if you square both sides, again you get x cubed is tangent squared, so this is really tangent squared plus 1. And we know that by an identity is just, well, secant squared. So notice what happens here is you have secant squared over secant squared, so those will cancel out, and that's really it. So maybe we can actually finish this off, but I'll have to write the answer over here. So using this substitution, maybe we can squeeze it in here. We get the integral of at radical x dx is equal to the reciprocal of this, so I'll pull the 2/3 out, times secant squared theta d theta. The denominator, coincidentally, is also secant squared. So those, notice, cancel out. So we just get, well, those cancel out, so we just get integral of d theta, which is just theta plus c. But now the only issue is how do we solve for theta? Well, basically I have to take tangent inverse of that. So really the answer is 2/3 tangent inverse of x to the 3/2, and then plus c. So that wasn't actually too bad. So instead of being an exercise on your own, I kind of did you a solid there. Maybe we can do the same here, but let's see. Now this one also, very similarly, I would like this to be a square. It gets a little iffy though, because if you force this to be a square, in this case it's going to be very similar, it's just going to be tangent squared. So you force this to be a square, you get x squared is equal to tangent squared, or x to the 4th equals tangent squared anyways. But then if you take the square root of both sides, you get this x squared is equal to tangent, so yeah, that's fine. But now notice that the derivative of both sides is going to be 2x dx, and then here this is secant squared theta d theta. Now the issue is we don't have an x on top actually. There's kind of a way you can do it where you solve for x here and you get radical tangent, and there's some things you can do. But there's a quick fix. There's a really quick fix. Good quick fix. It's to multiply top and bottom by x. So notice I add a square there, top and bottom by x, you get that. So notice these cancel back to what we had originally. And now we have the x dx to catch that part here. So now multiplying by 1/2, we get x dx is replaced with, well, 1/2 secant squared d theta, so we can pull the 1/2 out using this substitution. So pulling the 1/2 out, x dx is replaced with, again, 1/2 secant squared theta d theta. The denominator, well, x squared is tangent, so we're going to have a tangent there. And much like we saw here above, if x squared is tangent, x to the 4th will be tangent squared. And notice x to the 4th plus 1 is tangent squared plus 1, which is just secant squared. So we actually get cancellation of these. And this is really just cotangent. But if you want to write it like this, as of course cotangent is cosine over sine, kind of like how tangent is sine over cosine, then you can use a substitution. If u is equal to sine, then du is cosine theta d theta. So maybe I can use some space here. We end up getting 1/2 outside of the integral 1 over u du. Using the substitution, u is equal to sine. And that I think is pretty easy to establish because again du will be cosine theta d theta. And yeah, it's not too bad. And now of course the antiderivative of this is 1/2 ln of absolute value of u plus c. We have to back substitute twice, I think. First, u is sine, so this is going to be ln of sine of theta plus c. But now what's sine? Well, if tangent is x squared, I guess we have to make a triangle. So I can do that over here. I'll erase a lot of this work once we start these two problems. No, I'm going, I know, all over the place. But tangent, of course, in this case is x squared over 1. Since tangent is opposite over adjacent, we get that. So then by Pythagorean identity or Pythagorean theorem, it's this squared plus this squared is equal to the hypotenuse squared. The hypotenuse is the radical of that, which is x to the 4th plus 1. Notice it's just the original, well, radical, the original expression we had in mind, x to the 4th plus 1. And then we can say that sine of theta in this triangle is x squared over that. So it's going to be 1/2 ln of absolute value of x squared over the square root of x to the 4th plus 1. If you want, maybe you can use some logarithmic properties to simplify this in a little bit of a different way. But this, honestly, I think looks pretty cool. So, in fact, you can bring the 1/2 in. That would be 4th root then. And then, because you take like 1/2 to the 1/2 power, basically. And then x to the 1/2 would become just x. But I'm going to leave it like this, and I think this is really nice looking. Hopefully I didn't make any mistakes. I know I'm going kind of fast here. So now I'm going to erase all of this. I'll even erase these examples actually, and then we'll move on to these finally. So those previous examples were pretty challenging, but as it turns out, a challenging integral is pretty tricky because usually the challenging part is getting this started. Once you have determined a good strategy to use, and you have certain recognition points, of course, then the rest is kind of history. So once we figured out that they were just, well, essentially trig integrals, or trig substitution rather, then we can go from there. So that wasn't too bad once we had established the technique and the method to use. Here, it should be kind of obvious because inside of the radical we have 1 minus x squared. So maybe we can use trig sub. Let's see. So x would be sine. And trig sub always kind of works. It just gets a little hairy when you back substitute. And with limits, you would change the limits. Notice none of the problems in this section are limit problems, definite integral problems that is, because here we want to focus on just integrating. Evaluating you can do after, but notice when you evaluate, sometimes you have to change the limits with each substitution. So that I think is still an important problem, an important type of problem to try on your own as well. But notice if x is sine, then dx is cosine theta d theta. Okay. So this is all we need for a trig sub, just the original substitution and the differential. Let's see if we can apply stuff. So on top we'll get, let me see, we'll get sine theta times ln of sine theta. That looks a little funny. Over 1 minus sine squared is cosine squared. The square root of cosine squared is just cosine. So we'll leave it like that. So dx is actually cosine theta d theta. So the dx here will be replaced with cosine theta d theta. So that the cosines actually cancel out, which is nice. But now we're left with this weird looking thing. We have sine of theta times ln of sine of theta. And that looks really bizarre looking. And you may think, well, what if we just use u sub, let u equal sine, we'll have u times ln of u, and then we can use by parts maybe? But that doesn't work. It doesn't work because if u is sine, du would be cosine theta d theta, and we don't have a cosine here to catch that differential part. But by parts actually works. So let's consider by parts. So if we were to use by parts, we need a u and a dv to get the ball rolling. Now u is always going to be, remember, Liate. L in Liate would be natural log in this case. So let's try ln of sine of theta for u. And then dv would then be, of course, the other thing, which is sine theta, and then d theta. So that's okay because we can take the antiderivative. So that setup part is all right. You always want to make sure that your dv is such that you can find v, and your u is such that you can find du, but, well, notice differentiating is never an issue. Anti-differentiating is the issue. So derivative of this, if you don't know, there's a quick rule for natural log of something. It's just the derivative of the inside over the original inside. So notice this is just going to be a cosine theta over sine. D theta like that. And this is nice because, well, we get, let's see, we get uv, that's fine, minus the integral of v du. So let me write that down here below, I guess. So we're going to have cosine of theta times ln of sine, but then minus the integral of this times that, which will amount to cosine squared over sine d theta. Which seems a little annoying, just a little bit. How do we go from here? I guess we can split it up. We can write one, because u sub won't work. If you let a sine equal u, again, we have one cosine to catch it, but then we have a cosine left over, and then we get radicals involved again. Maybe it's doable, but I'm not going to even go there. I think what I'm going to try to do is use a trig identity. I'm going to write cosine squared is 1 minus sine squared over sine. And notice if you split this up, this is actually really nice. You get 1 over sine minus sine squared over sine is just sine. And this is just the integral part only. And this is good because we actually know the antiderivatives of each of these, kind of. The antiderivative of negative sine is negative cosine, so that part's going to be no problem. I know this is looking a little hand-wavy. So I have a minus, minus, and then minus this thing. Now, 1 over sine is cosecant. And this is something I mentioned before, specifically in 7.2, that I said hopefully wouldn't come up at all, and it's coming up a little bit here. And that was the integral of secant of theta. And this is kind of like a known fact, is that it's ln of absolute value of secant theta plus tangent theta plus c. Now, it's also kind of a known fact that secant and cosecant kind of behave the same, much like a tangent and cotangent kind of behave the same. So just like as an example, notice the derivative of tangent is secant squared. Well, as it turns out, the derivative, if you don't know, of cotangent is negative cosecant squared. So there's a lot of kind of patterns with functions and cofunctions when it comes to trig functions. And as it turns out, I'm going to spare the details, but you can check by taking the derivative and verifying it's indeed true. The integral of cosecant theta d theta is equal to, well, might as well write it here when we take the antiderivative. It's going to be negative ln of, much like this is secant plus tangent, this is going to be cosecant plus cotangent. Get a little more space. And this is minus cosine. And then plus c. Perfect. So I just want to make sure everything's lining up okay. It's looking all right, kind of. I say kind of because we have to back substitute and it's going to be a little crazy. So we have that cosine all the way in front of the minus here. We can distribute the negative, and when we do that, these all become positive. We don't need a parenthesis anymore. And then this is cosine theta times ln of sine of theta. Again, a little more room. There we go. And now I'm going to erase this, shift it up, and then back substitute. Right, so I erased everything and I shifted it up. I made a little bit of a mistake. I said that the antiderivative of negative sine is negative cosine. It's actually positive cosine. But the negative from the by parts distributes and that changes to negative. So there we go. So now we're going to write, and this should be cosine theta. Now we're going to write each of these in terms of x using our original substitution. But of course we need a triangle to make that happen kind of more easily. So notice sine of theta is equal to x over 1. So it's like that. And then basically the other side is just the original radical we have in our integral, radical 1 minus x squared like this. And now we can use this to evaluate all the other things. So cosine is, well, just the radical part over 1. And then ln of sine is just x, so that's ln x. Plus ln of absolute value of cosecant plus cotangent. Great. What's cosecant? Cosecant is the reciprocal of sine, which is 1 over x in this case. Cotangent is, well, that's going to be this over, well, tangent is x over the radical. Cotangent is the other way around. So it's going to be the radical over x. So we have the radical over x, like this. And then cosine, again, is just that radical part. And you could write this, you can try to simplify this a little bit maybe, using some log properties perhaps. I mean, specifically these combine, so I'll actually just do that combination part because I think that's not too bad to see and it makes it look a little nicer. So I'm actually going to leave it like this. Yeah, I don't want to, you could bring this in as a power and combine those ln somehow, it's going to look too crazy. So let's leave it like this, box that up, oops. Pass through the C there we go, looks a little better. And now on to the last example we're going to see in this section. So here, you can try thinking about this a lot if you want, but notice if this is 1 minus sine squared on the bottom or on top, then it would be solid. Because then we'd have 1 minus sine squared is just cosine squared, and then we can start to build up some progression there. So what I want to do in this case, I actually want to do multiplying by the conjugate of one of them. Now, where do I want the cosine squared to be on that comes as a result? Do I want it to be on top or bottom? So do I want to rationalize the numerator or denominator? Well, it's not really rationalizing, but it's kind of rationalized. As it turns out, I think we want to do it for the denominator. And I'll let you try that on your own to see. In fact, we'll see if it works out. So in other words, I want to multiply top and bottom by 1 plus sine theta. And I think we'll be okay here. Let's see. So now after doing this, we get, well, 1 plus sine, I said theta, it's really x. So we have 1 plus sine times 1 plus sine, so that's really a binomial squared. So actually, if you expand that out, we can get 1 plus 2 sine x plus sine squared. And notice in the bottom, it's a difference of squares, that's just 1 minus sine squared. And we wanted that, of course, so that we can write this as just cosine squared. So this is 1 plus 2 sine of x plus sine squared of x all over cosine squared of x. Perfect, dx. And now the magic part. Now we're going to split this fraction up and split the integral up, and I believe we can take the antiderivative of each term. Let's see. So we're going to get the integral of 1 over cosine squared plus 2 sine of x over cosine squared plus sine squared over cosine squared. Okay, I think we're making okay progress. It's cosine squared dx. Now, of course, you can rewrite these in a kind of a more sophisticated way. 1 over cosine squared is just secant squared, which we know its antiderivative is just tangent. So this guy's done right away. Yeah, so if we split up the integral after splitting up the fraction, we get this dx, integral of this dx, which is just tangent. So perfect, that's done. No substitutions or anything, so that's great, we can do that. Plus 2 times the integral of, so I'm pulling the 2 out of the integral and splitting it up. So notice sine over cosine is tangent, but this is cosine squared. So really you can write this as, if you want, sine over cosine, but then you have an additional cosine in the denominator. In other words, you can write this as sine over cosine times 1 over cosine, and notice that's just tangent times secant. Let me write it as secant tangent. And of course we know the antiderivative of that as well. The antiderivative of secant tangent is just secant, and it's 2 secant. Plus, the last thing here, of course, sine over cosine is tangent again, so this is tangent squared. And the antiderivative of tangent squared is fairly straightforward. I'll kind of show it here off to the side a little bit. Basically, I'm going to rewrite tangent squared as secant squared minus 1. And then you can clearly see that the antiderivative of each of these will just be tangent and negative x. That. So that's not too bad, it's just an identity. So this is plus tangent of x minus x, and then plus c finally. Now notice that tangent and tangent actually combine. So let me write this as 2 tangent, and then move a plus c over here. So this is a really nice example, I think. And a lot of these are all really good examples, but again, it's getting it started. So try it on your own to see if you can get it started in the same way, and see if you can keep the ball rolling, and if you can land somewhere like we have here. Awesome. So that concludes 7.5. One thing I kind of want to mention that the book includes 7.5 with, which is a really interesting and good thought, is that not every integral is actually doable. In fact, there are some things that are called non-elementary functions, which are basically functions that can't be written in exact form like these. Not exact form, but they don't really have nice names. And there are some nice examples the book gives. Some examples are like e to the x over x. So no matter how hard you try, that's undoable as it turns out. So we just call this, there's a name for this function. And then there's similar ones, like there's a 1 over ln of x. That's also not doable as it turns out. Another example would be something like sine of x squared, e to the x squared. These are all examples of integrals that have actually no antiderivative. It's funny, because if you consider the definite integral, they can actually be done, but, well, you would basically do them by approximation, which leads us nicely into the next section we'll be discussing, 7.7, which is a section on approximate integrals. We'll be taking a look at different rules, kind of like, if you remember from Calculus 1, where we consider like rectangles to approximate integrals. We'll be doing something like that, but a little more sophisticated. And we'll be skipping 7.6 because that's a section on basically computer-assisted calculus, which if you want to look at, it's kind of cool. But yeah, that's it for 7.5, so I'll see you in the next video for 7.7. It's going to be a lot of fun. Hope you enjoyed, and I'll see you then.